All right, welcome back to the Mathematics of Data Models, Lecture 19. This is a Northeastern University course, Code 2810, and I am Professor Wu. So today we're going to talk a little bit more about Gaussian distribution. So in the last class, we learned to recognize the most common probability distributions. And one of them was Bernoulli, where there's only two possible options, 0 or 1, right? So we learned this. And the idea of having a probability distribution is we can put the value of the event, like did 0 happen or did 1 happen? And then it will output very specifically the probability of that. So if we put 0 in here, it will tell us the probability that 0 will happen. If we put 1 here, it will tell us the probability that 1 will happen. So these were some of the distributions, like exponential, Gaussian, Poisson, that we looked into. Now, one of the most important distribution that we learned is the Gaussian distribution. Now, the Gaussian distribution has the equation that looks like this. And from the last class, we learned that as long as we know the mean and the standard deviation, essentially we can plug them in, and now we have the function itself. This distribution is also known as the bell curve, and very often we represent this distribution with this symbol. Okay? It's an N. It's an N. There's like a cursive N, where as long as you know the mean and over here is the variance. As long as you know the mean and the variance, you know this entire equation. Right? So this is often represented this way. Now, the Gaussian distribution is so important, it's used to model the majority of science. A lot of science is basically modeled by the Gaussian distribution. Now, to the right, over here, you can see that we have the SAT score being modeled by the Gaussian distribution. Right? Another one is the population. So blue is the male population height, and the red is the female population. So this Gaussian distribution is used so much because so much of life is basically you have something in the middle, right? And then it spreads out. Similar with height, the average height for male, like most people are a certain height, and very few people are like 7 feet tall. So because of that, like because of this pattern in life, so much of life is basically modeled with Gaussian distribution. Okay? Now, with the Gaussian distribution, over here, we call this the center, also the mean. So the average value is essentially the mean. And every single step outward, we call this the standard deviation, sigma. So what happened is, if you are one standard deviation out, the area here is 68%. So basically, if you're within one standard deviation, it's essentially saying that you're in the majority. Like majority of the people falls in here. However, if you include the second standard deviation, I believe roughly 95%. 95% falls in here. Right? So if you're in the 95%, then that's within two standard deviations. Now, as a reminder that a standard deviation is simply the square root of variance. From the previous class, we learned how to calculate the variance, so you also know how to calculate the standard deviation. Now, you might be wondering, how is it that so many things in life can be modeled by Gaussian distribution? And today we're going to kind of go over the theoretical reason why Gaussian is so important. But first, I want to distinguish the difference between a standard, between a Gaussian and a normal. Let's write Gaussian distribution and a normal distribution. A Gaussian distribution is one where you can just assume that there is some kind of mean, and some kind of standard deviation. So the only difference between really when you think of Gaussian and a normal distribution is that the normal distribution, the mean is 0. So if this mu is equal to 0, notice how this expression will become this. Also, standard deviation is equal to 1. So if that is equal to 1, then you just got a 2 here. Similarly, that will become 1. So that's only really the difference, right? That's it. Like, in general, if you just think in terms of Gaussian distribution, that's much more general, right? Gaussian includes the normal distribution. And once you have the Gaussian or the normal distribution, to find the probability between A and B, like probability that X happens between A and B, you take the integral, okay? So this one, you take the integral of the normal, and this one is the Gaussian. Now, if we're calculating the probability of a Gaussian, like I said, you could calculate the integral, but alternatively, it actually makes more sense to use the CDF. Now, if you remember, if you have the PDF, right, P of X, PDF, if you put an X value here, it will return the Y value. That's what a PDF does. However, CDF, when you put an X value in, right here, it gives you the area all the way till X. So CDF is often used in place of integral. Instead of calculating the integral like this, you just plug in the CDF if you're trying to find the probability. So if you're trying to find the probability between A and B, right? So this is point A and this point B. So if you find the CDF of B and then subtract the CDF of A, notice that will essentially give you the area. This way we can avoid calculating integrals. Like I just wrote here, probability between A and B is just the difference between them. Now, a long time ago, when I was learning about Gaussian distribution, which was in the 90s, back then we didn't really have Python, and it was really, really hard to calculate the integral. So the way I was taught was that we have this lookup tables in a book. So we would go to the book and look up the value B, and then you will give us the integral. And then look up the value A, right? And then we have to do the subtraction. So historically, we just didn't have Python and had to do this. And because we had to look into a book, it was a real pain. And you can imagine, depending on like the Gaussian distribution, right? If a Gaussian distribution is here, or it's fatter, or if it's like, so here's 0, here's 100. So this is a much bigger distribution. The area with the value you plug in is going to give you a different area. So from here, you can imagine it would be impossible to have a book of every single possible lookup table. Right? You will need a lookup table when the Gaussian is in the center. You will need another lookup table when the Gaussian is at 100. You will need another one for 200. So it was very, very difficult back then, because there's so many, the Gaussian could be anywhere, and yet you can not have infinite lookup tables. So you can imagine, depending on the mean and the standard deviation, the area would change, right? The area between x to negative infinity is very different from x to negative infinity for this distribution. So what we did back then is that instead of having infinite lookup tables for different mean and standard deviation, is we just transform every single Gaussian distribution into a normal distribution. So we just transform right here. Yeah, we just transform every single distribution into this. Once we transform into this distribution, this is the standard distribution we look at, and then we look at the lookup table. Once we look at the lookup table, then we translate it back. So that's how it was historically done. So for example, let's say if you have x is equal to 3, right? For a Gaussian distribution where mu is 3 and sigma is equal to 1. This is equivalent to x equals to 0 for a normal distribution. So a Gaussian distribution where x is equal to 3 with some kind of mean and standard deviation would be equivalent. And when we say equivalent, we're talking about the area, right? The area, CDF, will be equivalent, as if you have plug-in x. So this was the idea. When we will have a Gaussian distribution, and then we will need to transform it into this normal distribution, then we would do all the calculation. So nowadays, right, we don't have to do that anymore. We don't have to convert every Gaussian distribution into a normal, so just to have a lookup table. Instead, you can just use NumPy, right? And to find the x value, right, you can plug in the x value. So this is with a normal distribution, where mean is 0 and standard deviation is 1. Now, you just plug 1, and you automatically give that value to you, right? It will just give you 1. It will give you this value, right? Now notice, if we have a different distribution, where mu is equal to 1 and sigma is equal to 1. Well, if that's the case, we can put the mu and the sigma in conjunction with a value. So let's say you want to find the PDF at 2. Okay? If you plug the PDF at 2 with this, it will give you, again, P of x. Now notice, they're actually equivalent. Therefore, plugging a 2 into a Gaussian distribution versus plugging a 1 will give you the same result. So in a lookup, historically, we would have had to translate this into this value, then use the lookup table to get this. And it turns out that they would then be equivalent. But today we don't need to do that anymore. Now, but of course, normal distribution is still used a lot. Now, besides PDF, which would just give you the value, P of x, you can also do CDF. Notice, if you don't put the mean and the standard deviation in as the argument of the function, then it automatically assumed to be normal distribution. However, if you were to add the mean and the standard deviation, then it will take that into account as well. So if you want to find the area from -1, right? So here's -1. So this is going to essentially find the area here. Okay. Now notice, equivalently, if you have plug 0 here for the Gaussian, it will give us the same area again. Or if we plug 3, it's equivalent to 2 here. Notice that the area is the same. Now, if you want to find the area between 2 and 1, this is equivalent to 3 and 0. Right? Notice for each one of them, I did put the mean and the standard deviation, and they would still be the same. Okay? Now, to find the area, I want to specifically say that when you find the area, if you were to take so this is B, right? Notice if you find the area for B and then subtract the area for A, that will give you the area in between. Therefore, when you calculate the integral, you could just write the area from B minus the area from A. Okay, that's the code to make this happen. Now, CDF, like I said, if you plug a value B it will give you the area. You can do the inverse of a CDF. So f of x is CDF. But if you have an inverse, f inverse of x, right? So that means something else. So what you put is a percentage, 0.95%. If you would do that, it's going to return x. So, for example, if you want to know the 95%, you want to know the x such that the area contains 95% of the population. Then you will put this here, and then you will tell you the x value such that it will give you the 95%. Okay, so that's the CDF inverse. So, like I told you previously, to find the CDF, essentially, CDF tells you all the area from negative infinity all the way up to x. CDF inverse, it tells you the area and conversely give you x. So it does the opposite. And the command to do the CDF inverse is PPF. So norm PPF 0.5, right? So you know that this is 0. Therefore, half of the area, which is 0.5, will end up right here. So you should return 0. So if you return 0, it means that that's where the half of the area is. And you can see that it does. Or if you want to know 95%, which is right here, it will tell you that it's roughly 1.64. Notice over here, it follows the same convention. If you don't put in the mu and the standard deviation, it automatically assumes that it's normal distribution. However, if you put it in, take that into account, then it treats it as a Gaussian distribution. So you can now answer questions such as if you want if you want to score higher than 90% of the students, what score would you need, right? Because now you look at the percentage and it tells you what you actually need to achieve that percentage. Or if you say that 5% of the students score higher than you, then it can go tell you, you can use like PPF to identify. Then if 5% score higher than you, then what was your score? So, like I said, today, there's no longer a need to convert a Gaussian distribution into a normal distribution. Gone are the days where we had to pull up a lookup table that's really big, and then you have to kind of look through it. So, but even though we don't need to do the conversion anymore, understanding the conversion today is still useful, and it's used for many methods. So here, I have this distribution where the center is at 8, and if you were to do the conversion, this distribution will look like this. So notice, if you had the center at 8, that would be equivalent to the center at 0, where the area over here and the area here are identical. So knowing how to do the conversion is still very useful. The question we want to answer ultimately is that if we given some x value, right, for a Gaussian distribution with some kind of standard deviation, well, what is the equivalent z value such that the probability will be, well, no, such that, not this, such that the area would be the same. Okay, so you want the area here to be the same. I wonder if the probability is the same too. Maybe the probability is the same. I forgot. I need to look this up. But anyways, definitely the area. Okay. Now there's this technique called variational autoencoder, and they are basically using this idea of transformation. So you definitely want to learn the transformation still. So how do you perform the conversion? Well, it's actually a really simple equation. Whatever value you have, x, right? Whatever value x you have, if you just subtract the mean and divide by the standard deviation, that will give you the z, and that's it. So let's say you have a Gaussian distribution where the center is at 0 10, 10, and then standard deviation is 2. So this is a relatively fat one compared to this. And we want to know the probability that is less than 12. Okay? So 12, we want to know the area for green. So to convert this, right, we know the mean and the standard deviation, 10 and 2. And we know that we want to convert 10, so 10, sorry, we want to convert 12. We want the area to be below 12. So x is equal to 12, so 12 here. Then the equivalent z will equal to 1. So it's saying that 12 here for Gaussian is equivalent to 1 here, and that the area will be the same. Okay? So now you see that the area between, for the Gaussian distribution, all the way to 12, it's equivalent to the normal distribution to 1. Okay? Now also, let's also look at an example for SAT scores. So given an SAT score shown by the Gaussian distribution, it has a mean of 1,000, so on average people got 1,000, and standard deviation of 200. What score would you need to achieve in order to be the top 95 percentile? So what would the x be such that the area here will be 95%? Well, it's pretty easy. If you know the 95 percentile, you can do the inverse, PPF. You put the mean, and then you put the standard deviation, and it tells you the score. So you needed to score 1328. Now, this right here assumes that it's a normal distribution. Therefore, if you just put 9.5, it would have given you 1.64. Then you have to convert again using this equation, right? This is the z value. You know the mean, you know the standard deviation, and then you have to calculate for x. So you can imagine how painful it was for us to do these kind of problems back then. Now that you see, with z, you calculate for x, you get the same value, 1328, right here. So what this is telling you is then you need to score 1328 to be the top 95%. Okay. Let's see if you understand this idea, and by practicing. Let's say that you have the height of male, so blue is male, and red is female. So these are the height of the US population. And the male looks like this, female looks like this. Okay? So for the men, the mean is 70 inches and standard deviation 3 inches. So men, mu is equal to 70, standard deviation equals 3. And woman, mu is equal to 64.5 and standard deviation is 2.5. Okay, so you can see the two distinct distributions. Now you want to pause the video and pull out your laptop and see if you can calculate the percentage of male that are taller than 67 inches. Okay, so that would be whatever CDF is, 67, and 1 minus that, right? So 67 inches, the CDF will give you this area, and you want the opposite, right? What's the probability somebody is taller? So it should be opposite. And then what percentage of the female will be shorter? Well, then you use this again and see if you can calculate the percentage of females that are shorter. Now, what height would a male need to be taller than 95% of the female population? So now you need to use that PPF function, right? Now, this is actually quite interesting. If we make the assumption, Okay, so if we make an assumption where females would only date guys that are taller, right? So if females, again, this is assumption, not necessarily true, would date guys that are taller. Essentially, if you were to solve this question here, what height would a male need to be taller than 95% of the female population? So this would essentially tell you what height would a man need to be able to date like 95% of the female. Like this was I think this was one of the social science questions that I had, and well, it's not necessarily true, but it's just interesting for you to solve. Anyways, pause the video, see if you can solve it. We're gonna move on. Okay, so the first, let's look at the easiest version, which is just using a Gaussian distribution. Well, what's the probability that it will be taller than 67 inches, given that the average is 70 and standard deviation is 3? Well, this will give you the probability of shorter, and 1 minus that will give you the probability that you'll be taller. So here it is. And now, what is the probability that a girl is shorter than 67 inches? Well, the female mean and the female standard deviation here, and then this gives you the value. Now the last question is basically asking you want what is the probability 95 percentile for the female, given the female. So for the female mean and the female standard deviation. It turns out to be 68 inches. So for men who are 68 inches or taller, which is approximately 5'8", they would essentially be taller than 95% of the female. So that's not bad. Like 6'8" is an okay height. So you can solve it using Gaussian, and I think on your own time, you should definitely see if you can solve it with a normal distribution as well. Now, this I included here. I'm not really going to go through it. You want to study the code to see how I generated. So I was able to generate this plot. Here's the code that generated the plot. Okay, so these are just interesting plots that, for your own like usage, it will be nice for that you can plot it. Okay, so that is the part 1 of the lecture. We will continue later with part 2.